5.5 Normal approximations to binomial distributions. So in this section, we're going to be taking a discrete problem and converting it to a binomial problem and turn it into a normal problem. So binomials is what we did first in 4.1 and 4.2, and we're dealing with data that was discrete. It was 1, 2, 3, 4. That was it. No in between. Chapter 5, we went over to continuous variables, which means we had, the in-betweens. We had a lot of numbers, infinite number of numbers that we can choose from. So what if our binomial problem has a really, really high n, or a really, really high sample size? If that's the case, we can use a normal CDF function to solve a binomial problem. Okay, so if we have a really, really high n and it fits, we're going to use a normal CDF to do a binomial problem. If it doesn't work, then you have to keep with that binomial problem and continue with the binomial problem, doing it that way. Alright, so this is the phrase normal approximation to a binomial distribution. You'll see this somewhere, whether in directions, whether it's in the actual problem. Somewhere in your problem you'll see this phrase, and that'll let you know that you're doing the 0.5 thing. So how do you know if you do the 0.5 thing? So since this is not a normal problem, we can't use the central limit theorem. So we're going to have to use this. If n times p is greater than or equal to 5 and n times q is greater than or equal to 5, then the binomial random variable x is approximately distributed with, and this is how you calculate your mean and calculate your standard deviation. And this is from chapter 4. So you want to know where they're getting these from? Chapter 4 formula sheet. How do you calculate mean? How do you calculate standard deviation? It should be at the very end. So n times p represents how many successes do you have, and n times q is how many failures you have. Okay, so where n is a number of independent trials, so that's our sample size. P is a probability of success, so we've seen that before. And Q is a probability of failure. So we need at least 5 successes, 5 failures to do this pretty much. We need 5 successes, 5 failures to do our problem. So normal approximation to a binomial. As n increases, the shape of the binomial distribution becomes more similar to a normal distribution. Hence, we use continuous normal distribution, which is normal CDF, to estimate a binomial distribution. So that means that the more numbers, or the higher your n, with the histogram, we have bars, right? But as your n increases, those bars actually turn into a normal distribution or a curve. Okay, so that's what we're pretty much doing. We're saying that as your n increases, then your graph will start looking normal, or it has a normal curve to it. Alright, when you use a continuous normal distribution to approximate a binomial probability, meaning we're going to use normal CDF to solve a binomial or binom CDF problem, you need to move 0.5 units to the left and or right of the midpoint to include all possible x values. So we're trying to include any x value that will fall under that characteristic. And this is called continuity correction. It's called continuity correction. So let's look at some examples of that. Lined up, okay. So in the problem, it will say it will be a binomial problem, but then we're going to have to convert it to a normal problem. And we have to take note if we're going to include the actual answer. So exactly, remember, normally when we did a binomial problem, we did binomial PDF. So exactly C means we want any number that will round to that number. So let's say our C is 8. So let's say we're dealing with x equals 8. So what numbers round to 8? 7.5, 7.6, 7.7, 7.8. Those round to 8, as well as 8.1, 8.2, 8.3. Those round to 8. So that means that we're going to add and subtract to get our probability. Subtract 0.5. Forgot that part. So it'll always be a 0.5 somewhere. So don't get too technical. Oh, wait a minute, that rounds to 9. Or, oh, that does round to 8. That doesn't round to 9. Just use the 0.5 rule. Okay? So you'll have equal signs. Well, you could have equal signs included on this side, but in the middle with normal CDF, notice we don't use any equal signs. That's because we don't use them for normal CDF, only for binomial. So includes C just means that we want that number. So at most C. At most C means the most I want to include is that number and everything below. That's at most. The most I want to include is that number and everything in below. So let's say we still have that same 8, but now we're doing at most. So I want 8, 7, 6, 5, 4. I want everything below 8, including 8. That's why it's included. So at most means I want that and below. So I want any number that rounds to 8 because I want 8 and below. So that means we're going to add 0.5. There's a little trick that goes with this. I'll teach it if I can remember it. I didn't come up with it. One of my students came up with it a while back. So if I can remember it, I'll teach it to you. So at most means I want 8. I want any number that includes 8. So I'm going to add 0.5. Fewer than C means I want the numbers below that number, but I don't want that number. So if we're still dealing with 8, I want all the numbers below 8, but I don't want 8. I don't want anything that rounds to 8. So I can't add 8.5 this time, because if I add 8.5 and I look at all the numbers below 8.5, 8.4, 8.3, 8.2, 8.1, all those round to 8, and I don't want 8 according to this, because fewer than C or fewer than 8 means I don't want it. So that means I'm going to subtract. And next, the problem is going to say at least C. So at least means I want that and everything above it. At least C means I want that and everything above it. So at least C means that I want this number. That's my lowest number I want. And everything above it. So because I want anything including 8, if I add 8, I'm going to skip over. If I add 0.5, I'm going to skip over 8. So if I add 0.5 here, but I do want 8, when I go 8.5, 8.6, 8.7, when I'm going up, I don't see the 8. So this time I'm going to subtract 0.5. Because I want all the numbers that include 8 and up. Include 8 and up. Alright, more than C. More than C means I want that. I don't want that number, but everything above it, that's what I want. So I don't want that number, just everything above it. And that's why that equal sign and not equal sign is there as well. So this means I don't want the number, but I want everything above. This means I want everything above and I want the number. So this time I don't want 8 to be included, so I'm going to add the 0.5. So notice, whatever your number is, whatever your C is, you only have two options. You only have the subtraction or the addition. That's it. So here's your shortcut. Let me make sure I get it right. So when you are looking at your probability, your what's this called? Inequality. Sorry, it's late. We're looking at inequality. If it includes a number, then we're going to choose a number. If it doesn't include a number, we're going to choose that number that the arrow is pointing to. So this is fewer than C. I don't want C, so I want to choose a number on the left. This is more than C. I don't want C. I'm going to choose a number on the right. And then it's going to be opposite when we have the equal sign. All right, let's try that. So let's match the binomial probability statement with this corresponding normal distribution probability statement. So this is what it is as a binomial. See my equal signs? This is how we correct it. So since my C is 109, my choices are 109 minus 0.5, 109 plus 0.5. Those are the only two options I have. And I have to figure out which one am I choosing. So let's look at number 5. You can use your shortcut now if you like. But I'm going to talk about the logic behind this. So I want all the numbers. Remember, this side is how I'm moving. So that's what I mean when I say I want all the numbers. I want all the numbers greater than, this is my sign, 109, but I don't want 109. Greater than 109, but I don't want 109. I need to skip over 109. So if I'm going greater than 109, and I'm starting here, 108.5, 0.6, 0.7, 0.8, 0.9, 109. So this includes 109 when I'm going up. But remember, I don't want it. If I start here, 109.5, 0.6, 0.7, 0.8, 0.9, 110, I never include 109. So this is why I'm going to choose A. Because I don't want to include 109 in my answers, in my X's. Okay. X is greater than or equal to 109. So this time I do want to include 109. I do want to include 109. And I want all the numbers above 109. So I do want to include 109 and all the numbers above. So this time I'm going to choose this one, because when I start counting up, I do include 109, and I do want it because of that equal sign. So the sign is always going to point to the same direction. So these were greater than, so I had to choose between those two. But then I had to figure out which one do I need for the number. So for these, they're both going to be less than, because they're less than in the beginning. But I have to choose which number that I want. So this is less than or equal to. Less than or equal to 109. So I want 109 when I'm going down. So this less than means I'm decreasing. And when I decrease, I want to decrease and include 109. So if I'm here, and I choose this one, and I'm decreasing, I don't have 109 in my numbers. Because I start 108.5, 0.4, 0.3, 0.2, 0.1. I skip 109. And I don't want to do that. So that means I'm going to choose this one. Because when I go down, 109.5, 0.4, 0.3, 0.2, 0.1, 109. I do have 109 and I want 109. Okay. That leaves us the last one with B. So to make sure we're good though. So I want all the X's less than 109. But I don't want 109. the number is less than 109, but I don't want 109. So 109 is not in here, but 109 is in here. So I don't want it, so I'm going to choose this one. It'll take some practice, so make sure you pause, rewind this again if you need to, and practice this. Go to your book. If you know the extra problems in the back of the book, the back of each section, you have your answers in the back of your book. Go through that, practice if you need to. Now to the probability. So approximating that binomial probability. So we're still going to use normal CDF because we're in probabilities, using probabilities and using normal CDF. Our lower bound and upper bound, negative 10,000 or positive 10,000, or whatever our correction is. The mean is going to be n times p. Remember, we don't have a mean. Well, they don't give us one in the problem. So we're going to have to find our own mean using n times p, which is the same thing we use to check our problem. And then square root of n times p. Oop, you can't see that. Mean n times p, and then square root of n times p times q. Okay, so our negative 10,000 or positive 10,000, depending on whether doing left or right. And then this is going to be our 0.5 n times p, and then square root of n times p times q. So in the directions, I don't put these up here, but out of the book it says use normal approximation to a binomial distribution. So use normal approximations. That whole statement. Use normal approximation to a binomial distribution. So it says it in the book. I just forgot to write it. So I'm put it up top so we can have it. Alright, so in a survey of high schools in a certain state, it was reported that 40% of students failed at least one class taken through distance learning. You randomly select 45 students from the state and ask them whether they failed at least one class through distance learning. What's the probability that fewer than 20 of them respond yes? Okay, so let's look at our N, our P, and our Q, and we can determine whether we can do the problem or not. So N is going to be 45. P so our P is our passing rate, 0.40. Our Q is the opposite of this, so 1 minus P is Q. So 40% of students failed. That means 60% didn't fail. So that's the opposite. Okay, NPQ. So we have to check to make sure we can do our problem. N times P is 45 times 0.40. Which is also our mean. So we have 18 successes out of the 45. Everybody else is a failure. So 0.6. Remember, failure does not mean bad. Let me just say that. Failure does not mean bad. It's just not what we're looking for. I like to add those together just to make sure I have my successes and failures. Everybody's accounted for. That is 45. forgot to write ink. 45 times 0.60 equals 27. We do that. So at least 5, we can do our problem. Now to find our probability. So the probability that fewer than 20 of them respond, yes. Fewer than 20. So does that include 20? Fewer than 20? It's like 19, 18, 17, 16. So now I have to correct this. Is it going to be 19.5 or is it going to be 20.5? So fewer than 20, I want below 20, but I don't want 20. This includes 20, this does not include 20 when we're going below. So we want this one. So we correct this to 19.5. Okay. So here we go. This is our probability. It's less than. So calculator first. Less than means we're going to have a negative 10,000. Then 19.5, because remember we want everything below this. Our mean is going to be 18. Then, okay, I'm not sure where I stopped, so normal CDF probability. Oh yeah, I was saying that n times p is the same thing as the mean, which is the same thing as the mean that will go here, and then we're going to put the entire standard deviation in the calculator, just like this. I'm putting parentheses just because on the paper I didn't want you to mix it up with anything else. But we're going to put it in just like this. Of course, I'm going to give you the table. So normal CDF, because this is a binomial problem. Here we go. Binomial problem, but we're using normal CDF to solve it. So negative 10,000. 19.5 is our boundary. Our mean, and you could put 45 times 40 in there if you like, and then square root of 45 times 0.60 times 0.40. Again, I didn't put parentheses in the calculator because I really don't need them. I just needed them on paper so you can see that that was a decimal and not a multiplication symbol. Alright, 19.5, 18, 45, 6.60, 0.40, 0.6760. 0.6760. So be careful with that rounding. So my tables. So for the table, we're going to do the same thing. Can you believe it? X value that's given with our probability minus the mean divided by standard deviation. So our X value that's been corrected minus our mean divided by our standard deviations. So 45 times 0.60 times 0.40. We're going to get that Z. We're going to use it as is because we have a left problem. We're going to use it as is because it's a left problem. So I'm going to put it in all at once. So I'm going to put parentheses around this. Around my numerator, divided by. You can do the one part and then the other part, but I'm going to try to do this all at once. It's 45 times 0.60 times 0.40. Again, this gives us our Z. And we're going to use that area as is. So 0.46, 0.4, 0.46. So 0.6772. 0.6772. So this is the calculator, this is the table. Next, a study found that 52% of U.S. drivers who use both alcohol and marijuana admit to driving aggressively. You randomly select 200 U.S. drivers. So if this were a central limit theorem problem, would be good, but it's not central limit theorem, so we got to check this. N times P, N times Q. 200 U.S. drivers who use both alcohol and marijuana, and ask them whether they admit to driving aggressively. What is the probability that at least 100 drivers will say yes? So N, P, N, Q. We got to check that. N times P, N times Q. So N times P is 200 times my passing rate. So out of the 200, 104 are successful. 96 are. All I did was 200 minus 104. I did it mentally, but I'm going to prove it. 200 times 0.48. Remember, all we do is subtract 1 minus 0.52. So we have enough success, have enough failure. Now, our probability needs to be corrected. So we want all the x's at least 100. So that means 100 and above. At least 100, 100 and above. So am I going to subtract 0.5 or add 0.5? Because I want 100 and everything above. This does not include 100. This does include 100 because we're increasing this time. So we want this one. If my paper gets off, I can't see what I'm writing. So when I pause, normally I'm looking backwards to make sure that you all can see what I'm writing. So we could do our problem. We corrected it. We got normal CDF greater than means that this is the smallest number. Then we got our 10,000, our mean of 104, and then our standard deviation. I don't know why I keep writing this backwards. It's fine. Multiplication is commutative, so it doesn't matter. So we got normal CDF 99.5, 10,000, 104, and then the square root of 200 times 0.52 times 0.48. Remember, if you need to pause this to catch up, please do so. .7379. On a table. Of course, you're not writing both of these, just writing the one that pertains to you. Now, the table, we're going to have to do the opposite because it's greater than. So whatever we get for our z, look at the area, do 1 minus that. So to calculate z, we're going to have to do the x minus the mean, or the value minus the mean, over standard deviation. So still the same formula. So our x now is 99.5 minus our mean of 104 divided by, remember, standard deviation is the square root of, so it's going to be, sorry, it's like stuff falling. It's going to be the same formula right here. So we're just going to rewrite it. So this is square root of 200 times 0.48 times 0.52. I'm going to put that in the calculator, find out what that z is, look at the area on our table, and do the opposite. Remember, doing the opposite again because this is on the right side. This is a greater than problem. So 99.5 minus 104. I'm doing the top divided by parentheses. You can't put it in all at one time again, remember. But I'm going to do separate ones because that's the safe way to do this. That's a safe way. It's going to be 200. Actually, I forgot my square root. There we go. 200 times, okay, there we go. Got to get back on the square root. 200 times 0.48 times 0.48 times 0.52. Close the parentheses. So notice it's outside of our square root. So just make sure it's on the right way. It's on the right thing. So negative 0.64 is what we're going to be looking for on our table. Get my handy dandy table. Again, this is for those who are using the table. You don't have to do both. You can do calculator or table. You can learn both if you like, but you know, just stick with the one and get proficient at it. So this is a negative 0.6. There's the 4. .2611. So area or probability is 0.2611. And we have to do 1 minus this because, again, we're going greater. We're going greater. 1 minus 0.2611. 2611. 0.7389. Again, it is going to be a little off because we're using the paper. The paper is finite, and the calculator calculates everything more efficiently. All right, last one. A study of former National Football League players found that 12.3% have undergone knee joint replacement surgery. You randomly select 100 former NFL players and ask them whether they have undergone knee joint replacement surgery. What's the probability that exactly 15 will say yes? Exactly 15 will say yes. So N times P, because we should be at the point now we can just identify our numbers. N is 100. Our P is our passing rate of 0.123. N times Q is 100 times, so whatever's left over from this, 0.877. Let me just double check that. 1 minus 0.123. Yeah, try not to do that too many times in your head, because it's going to be a little hard after a while. So 100 times 0.123, 100 times 0.877. We can do our problem. I have at least 5 successes, at least 5 failures. Alright, so for our calculator first, well, for both I guess, let's find our probability. So it says exactly 15. So exactly 15 as a binomial, when we convert this or correct this, exactly means we're going to do both. When I say do both, we're going to add 0.5 to both sides. That's going to be our boundary. So exactly means we want the less and the greater. So that means we already have both of our boundaries, because it's going to be a center or in the middle. So 14.5, 15.5. Then times, then N times P, or 12.3. And then our standard deviation. So square root of 100 times P times Q. So here we go. Second vars for normal CDF. Again, this is a problem that's a binomial problem. Just to give you time to find if you need to. A binomial problem. We're converting it to a normal problem, normal CDF or normal curve type problem, because we have a high N. Alright, so we got 14.5 to 15.5 as our boundaries. 12.3, which is N times P, or our mean. Remember, the same thing that we checked to make sure we can do the problem is our mean. So square root of 100 times 0.123 times 0.877. Close that parentheses. So 0.08, no, 0.0865. My calculator people, you're good. You're done. For my table people, so with the table, you're going to have to convert both of these z's these x's to a z. So you're going to have to convert both x's to a z. Then we're going to subtract those areas. Alright, here we go. So I call it z1. We're going to do 14.5 minus our mean over the square root of, and notice I'm not finding these numbers and then like plugging them in. I'm not finding what that number is. I want to keep the integrity of the problem. So I want to put the whole entire thing in at one time. So I'm not finding it part by part. I'm putting them all in at the same time. Luckily, we can just take this and then copy and paste it in a minute. So if we do it this way, (14.5) minus 12.3, close parentheses, divided by open parentheses, square root of 100 times 0.123 times 0.877. Get out of the parentheses, out of the square root and close it. I'm doing this so I can keep the integrity of my problem. So see how all that's under the square root. I hit the right arrow to get out of the square root. So this one is 0.67. Z2, because I put it all in at one time, I'm going to hit second enter and then change that number. Second enter, which copies what I just put in, or you can go up, hit that, hit this, hit enter, and it will copy and paste as well. So all I did was second enter, and I changed this number so I can get my second z. 0.97. I'm going to take these two z's with the areas and just subtract. So those who like to use that chart, hopefully you're following me. If not, email me if you are using the table and you are not getting it, because it's it's a little different when you use the calculator. The answer is a little different, but the answer should still be around the same answer. So if you're not getting these, please email me and let me help you. Okay, so both of these happen to be positive. Let me go on my positive side. (0.67) is 0.7486. This one should be bigger, I think. That's why I'm just putting it down here. We're going to subtract that smallest from highest. 0.97. It's about to get off. 0.8340. So I'm just going to subtract those two, highest from lowest. (0.0854). So remember, you are not doing both, not unless you really want to. This is the calculator and this is the table. Stick with what you know. If you like using the table because you're comfortable with it, stick with it. If you like using the calculator because it's quicker, stick with it. So there is no right or wrong way. And of course, if you like to use your StatCrunch or your Excel, you're free to do that as well. And if you choose to do one of those options and you need help, please email me or contact me as well.